We only have a few minutes of actual content left in the module. So we're going to back up a little bit. We'll go from, let's go to the more complicated. We'll start reviewing the more complicated. 156 is where we're going to pick up today. Back up just a step, go back to the more complicated Lewis structures, and then move forward through the end of the module. Then after that, we'll start going over last Friday's homework. Okay. What's going on with the 5 out? Do you guys know? Is it group strep or something, or? The 5 people we're missing today. The 5 people that are all separate.
Jayla's problem. I think Jayla wasn't feeling well yesterday. He's prone to sickness.
Okay.
Every year Kyle's like, who else is missing? It's Kyle, Jayla, Ike, Emily. Who's the 5th? Dylan.
Yep.
Ew. Dylan. I have no idea.
All right, so for a quick review, we're going to use these two molecules as part of our discussion at the end about the practical application of the strength of bonds, application of structures. We talked about a couple of homonuclear diatomics. Remember what the homonuclear diatomics are? Just homonuclear diatomics, where they are over here on the chart and what they represent. Yes, ma'am? So nitrogen, oxygen, column 7. So nitrogen, oxygen, fluorine, chlorine, bromine, iodine, astatane, and hydrogen are the homonuclear diatomics. Hydrogen, then the number 7. Nitrogen, oxygen, fluorine, chlorine, bromine, iodine, astatane. They are the elements which, when they occur naturally, they occur as molecules. You find them as molecules, not as individual atoms. If I told you to go out and get a sample of sodium, for example, or a sample of calcium or aluminum or any other of these other elements, you would anticipate that as you looked at that sample, whether it's solid or gas, as you looked at it, you would find individual atoms of sodium and individual atoms of calcium and individual atoms of aluminum, or whatever the element is. You'd find individual atoms of those things in the sample. For the homonuclear diatomics, if you have a pure sample of those elements, you do not find individual atoms of hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and acetane. You don't find individual atoms of them. You find molecules of them, which are formed by 2 atoms of the same element. So you would expect not to find hydrogen, individual atoms of hydrogen in your sample. You would expect to find individual molecules of H2. Hydrogen occurs as a molecule of hydrogen, not as an atom of hydrogen. Understand the difference? An atom has a single nucleus with electrons in different orbitals. A molecule has 2 atoms that are bonded together in some way. So hydrogen would be 2 hydrogen atoms bonded together to form a hydrogen molecule. So if you have a sample of hydrogen gas, it would be H2 molecules, not hydrogen atoms that you'd find. In the same way, nitrogen. If you had a sample of nitrogen, if you had a question that said you have 3 liters of nitrogen gas, you would not anticipate finding individual atoms of nitrogen. What you would anticipate is individual molecules of nitrogen, which is formed by 2 nitrogen atoms bonded together. So it would naturally occur as N2. Now that does not mean that you can only use combinations of 2 when you make other compounds. Okay? To make another compound, for example, H2O is not two H's and an O because H is always occurring as a double. It just works out that way because we also know that oxygen, for example, is a homonuclear diatomic. In naturally occurring oxygen, you're going to find oxygen molecules, not oxygen atoms. However, you can make carbon monoxide. Okay? So you can take this building block, these two building blocks of oxygen as an oxygen molecule, break it up and use one of them in combination with another element. But naturally occurring, if two oxygens are there unbonded to anything and they're in proximity to one another, they're going to form a relationship and form a molecule. It just naturally occurs. Because if you remember, oxygen has 6 valence electrons. Because we look over to the A columns, column 6A, there's our oxygen, 6 valence electrons. Let me go ahead and put them like, let's see, 1, 2, 3, 4, 5, 6. And another one next door has the same 6, let's say, mirror image of each other. 6 valence, they're in proximity. Each one is now on the hunt for 2 more, right? Each one wants to have 2 more electrons. It can get 1 more electron by forming this pair here. If it donates 1 down from each side, now it has 8. So if 2 oxygens are in proximity, they're going to find each other, come together, and form the molecule of oxygen naturally. There's nothing is required of you to make that happen. This will happen. We're going to see later on in today's lesson how naturally occurring these will be broken up. But what's really cool is through the energy of light, they get broken up. But then because they naturally form a bond, they come back together again on their own. So there's a continual cycle, a process of breaking up and coming together, breaking up and coming together that happens. And they come together not because there's energy being added to them to make them do that. This is the way that they naturally would occur. And so every homonuclear diatomic wants to and occurs naturally as a molecule of that element, not as an atom of that element. Okay. So we look at the more complicated ones. We just did oxygen. Oxygen is not a single bond. Oxygen is a double bond. There are 2 pairs of shared electrons between the two. So there are 4 electrons in play. 4 electrons that are being shared, forming a double bond. And as we get more sophisticated, as I said, you're going to learn, especially as we go into the other modules that talk about geometries, that these electrons repel each other and they more technically form like this. So there's about 120 degrees between each one. But for now, if you write it like this, I'm happy that there's 2 double bonds and 2 pairs of unbonded electrons around that oxygen atom. Okay. Now they also use another example, taking it one more level up, is with nitrogen. Nitrogen, as we said, is a homonuclear diatomic as well. Nitrogen is a little bit interesting because it has 5 valence electrons. It's column 5A. So nitrogen has its 5, and when 2 nitrogens are in proximity to one another, there are 2 nitrogens with 5 Lewis dots around them. Okay? I'm telling you it forms a molecule of 2 nitrogens, so we have to now figure out what does that look like. Well, I can take these 2 unbonded and bond them. Now I've got a semblance of a molecule, right? They're bonded together. How many electrons does each nitrogen see in its valence? 1, 2, 3, 4, 5, 6. Not enough. We're going to go ahead and clean up the unbonded electrons and try to bring them together to form bonds. So I'll bring this one over, bring this one over, bond them. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Still not there yet. I'll bring the other unbonded electron over, share it. Now, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. They both see 8 electrons. But again, because of the charges repelling, these are going to go to the outside, away from the bonds. And that is technically the way the Lewis structure for nitrogen should look with a triple bond. Yes, ma'am? No, because it'll eventually clean up. When it's right, it'll all clean up. And whether you show them, for example, you'll have others where there's one, like I said, right now, putting the two unpaired, unbonded electrons away from the bonds is technically more appropriate. Where you're at right now, if you were to do this, just for symmetry, I would take that, okay? But your next module, it's going to become much more significant that you realize that they would push away from the bonds because of the negatives pushing away from the negatives. That the pairs stay together. So this represents, for example, two electrons in, let's say, over here for nitrogen, these might be the the s orbitals, and these are the bonded p's. Something like that. Just one way to think of it, okay? So we've got oxygen represents a double, nitrogen a triple. And in the book, through the process he uses, remember when you have more than one atom, you're going to put the one that has the most unbonded, unpaired electrons, the highest number of unpaired electrons in the middle. Put the other elements around it, form single bonds, and then start placing all your valence electrons. Technique in the book, the way I do it, slightly different, but they get you to the same ends. Okay? Pardon? Does it? Okay. At times, remember how we were talking last night about how electronegativity is going to be very significant? Okay, electronegativity is going to start to play much more significance when we get into bonding and three-dimensional shaping and geometries and things like that. But right now, okay, how many, at any given moment in time, this nitrogen on the left side of the diagram, okay, at some times it has 8 electrons. And when it has 8 electrons, it would have a negative, what? 3, right? Right, because it has 7. It's got 7. I'm wrong, excuse me, 7, so it's got a 7, right? 7 electrons total. At times, though, it sees 8, right? So it would have a -1 charge. But when this side has a -1 charge, what does this side have? +1 charge, right? Because when this one is getting all 8, this one has 6, right? Because we haven't added any electrons. There are still only 14 electrons in play. When this side has 8, what is 14 minus 8? 6, right? So when this side has the extra electron, this side is down an electron. So when this side is -1, this side is +1, and -1 and +1 form a molecule that's neutral. And then when this side has the extra electron, it's negative. This side is lacking an electron, it's positive. The negative and positive neutralize each other so that the molecule has a net charge of 0. So your net charge is going to be 0. Your instantaneous charges, which we'll get into later, next module, goes back and forth. You can think of it as the charge is always flipping back and forth, like an oscillating current, you know. If you think of it as a figure 8, whenever the electron is on one side, that side's negative, the other's positive, and then it switches back over. That side's now negative, and the other's positive, and goes back and forth, back and forth, back and forth. Okay. So the net charge of this molecule is neutral, which is why this now is stable. This nitrogen molecule is not looking for anything else to bond with. There's no more chemical reactions that are going to take place naturally without adding a lot of energy to it, the activation energy to get this thing to do something. It's stable. This is oxygen is stable now. And if over here we use the example of chlorines, chlorines have 7. Single bond, they both have 8. They're stable. Okay, so this is single bond, double bond, and triple bond. And part of what we closed with yesterday was just this real brief statement I made that each one of these has different levels of strength. Think of the bonds as cords or chains that are holding them together. They're all of equal strength individually, but this one has 1 bond, 1 chain holding them together. This one has 2 chains holding them together. This one has 3 chains holding them together. Which one is the strongest bond? The nitrogen, the triple bond. The triple bond is stronger than a double bond, and a double bond is stronger than a single bond. Another way of saying that is a triple bond takes more energy to break than a double, And a double takes more energy to break than a single. Okay? So, that leads us into the last segment of the module. Before we do that, though, let's go through example 4.6 and take a look at a few more examples of these more complicated bonding. Example 4.6 on 158. Determine the Lewis structure for carbon dioxide. So just kind of walk me through the process. Carbon dioxide. I know my formula is CO2. And I'm going to look at that. Part of me says, okay, the next step would be look at the different individual elements that make it up, making up with bicarbons and oxygens. Okay? Now, carbon has, we've already learned, carbon is a column 4 element. I'll go ahead and close this again. Just trying to get some cool air up here. I don't know how you guys are keeping those fleece on. But carbon and oxygen. Carbon has 4 unbonded electrons, right? It has 4 valence electrons, which is like the perfect building piece in the middle. It's got all these areas, the things to connect to. Oxygen is a column 6, so oxygen has 2 unbonded electrons, not 4. I also can look at this in terms of symmetry. And the way God created things is very symmetrical, right? I've got 1 carbon and 2 oxygens. Doesn't it make sense that the carbon would be in the middle so it can have a mirror image? It would be symmetrical. That is the way it works out. Carbon has 4, oxygen has 6. I need another oxygen over here with 6. Start forming my molecule by bonding the central atom to the external atoms. So I need this, just to even make a molecule, I need that, and I need that, right? Now I've got something to work with. I'm not saying I'm done. I'm saying now it's actually a molecule of some sort. It might be incorrect, but before I just had 3 different atoms. Now I've got a molecule. Looking at the bonds, what does carbon see? 1, 2, 3, 4, 5, 6. It needs more. Oxygen, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So everybody needs more bonds, right? Let's start shifting our unbonded electrons towards each other. I'm going to move this unbonded over here and this unbonded over here and bond them. Take this unbonded and put it over here. This unbonded and put it over here and bond them. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. I formed 3 octets by sharing the electrons. So that is the Lewis structure for CO2. And again, this is good. Offsetting those is better. What I'm looking for is a central carbon, external oxygens, double bonds on both sides with the remaining paired electrons. Any questions on CO2? Again, it's a nice symmetrical molecule. What you do on one side, you do to the other side. It works out. We're going to do one very shortly, doing ozone, which is not, it's only made up of oxygen, but it's not symmetrical. So that'll make more sense in a little bit. But for this nice symmetrical CO2, there are questions on how to form the Lewis structure for carbon dioxide. The next example in the book, HCN, we've got a hydrogen, carbon, and a nitrogen. How many valence electrons are there in hydrogen? Just one. Just one. Valence electron. So there's 1 in hydrogen. Matter of fact, to make it kind of easy, I'm going to assume it's going to be on the inside, but for now, okay, that's fine. Carbon, we've already said, we're going to say repeatedly, carbon has 4. Shouldn't really have to think about carbon. 4. Nitrogen, how many unbonded electrons does nitrogen have? Well, it has 5 valence. How many unbonded? Unpaired? 3, right? Because if we count up 5, 1, 2, 3, 4, 5, there we go. We've got 3 singles and a pair. Okay. Now, one of the tricks you're going to run into, which tends to always work, is put your paired on top. So by convention, I usually put my 2 there, and 1, 2, and 3. So those are the Lewis structures for hydrogen, carbon, and nitrogen. Which one has the highest number of unpaired or unbonded? Carbon does. It has 4. Nitrogen only has 3. Hydrogen only has 1. So carbon is going to be in the center, just as I depicted it here. Now I'm going to go ahead and move my unbonded electron, an unpaired electron, around to kind of put it, because I'm anticipating a bond, right? Let me go ahead and bond to form a basic molecule, which may not be done, but it gives me a starting point. Let me bond those electrons. Right, so now we've got hydrogen, single bonded to a carbon, single bonded to a nitrogen. Now, is hydrogen done? Yes, because remember, its octet, it's only striving for 2. And it has 2 by sharing that 1 electron. This bond represents 2 electrons, so hydrogen is satisfied. It's done. Carbon and nitrogen. What does carbon see? 1, 2, 3, 4, 5, 6. It needs to pick up 2 more electrons, right? Nitrogen. 1, 2, 3, 4, 5, 6. What does it need to pick up? 2. Carbon needs 2. Nitrogen needs 2. Okay? We bring an unbonded and an unbonded unpaired. Okay? We're done over here. Carbon. 1, 2, 3, 4, 5, 6, 7. Needs 1 more bond. 1, 2, 3, 4, 5, 6, 7. Needs 1 more bond. We bring an unbonded unpaired. Unbonded unpaired. Boom. Now looking at it. Nitrogen. 1, 2, 3, 4, 5, 6, 7, 8. Carbon. 1, 2, 3, 4, 5, 6, 7, 8. Hydrogen. 1, 2. It's done. So we've met for all 3 of them. That is right. Now technically, what would I do to make it even better? Take my pair and bring them away from the bonds, because they're going to be repelled by the bonds. And that is my Lewis structure for HCN. Go ahead.
How would you do it if you had like more than 1 hydrogen? Since they only need 2.
Mm-hmm.
Like, 'cause I was confused on the practice problems on number 10, C2H4.
That's your molecule, right? C2H4. So carbons and hydrogens, of those 2, which one has the highest number of unbonded, unpaired electrons? Carbon. If you see carbon, it's going to be carbon, okay? So we're going to start by putting the 2 carbons together. Now, let's just do it. Now I've got 4 hydrogens. One, two, 1, 2, 1, 2, 1, 2. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. No, no, no. There. Symmetry, right? Nice symmetrical. And then technically, again, looking at the geometries, where would we go from there? How could we make that even better? This is right. This is right for where you're at now, Lewis structures. How can I make it even technically better? These are going to be all equally offset. So rather than having it be like an L, it's going to look like a tripod. Pardon? Okay. So again, just start from your center. Carbons have the most. Carbons go to the middle. Hydrogens go to the outside. Look for symmetry. That's a hint. I'm not saying that's every time, but it's a hint. Look for symmetry. Because if symmetry is there, God is the one who ordained that symmetry. So if it has a 2 and a 4, I know basically I'm going to end up being, cut it down in the middle. It's going to be a mirror image of itself. You fold it in half. Yeah. You may. Let's go ahead and consider the last part of the module, and then we can go back and review these kind of questions from the first homework from last Friday. All right, so they mention in here about an application of our discussion on energy from light. Talk about light being pure energy, whether particle or wave, the duality principle, but has energy. And the higher the frequency, the more energy, right? Remember that? The higher the frequency, the more the energy. Another way of saying that is the higher the frequency, the lower the wavelength, right? So the lower the wavelength, the more the energy. We're going to consider 3 different gases that are in our atmosphere and how they provide protection for us, naturally occurring protection from the energy that's coming towards the Earth from outside the Earth, from the solar system. All those different kinds of energy that's coming towards the Earth. How does it protect us? We're going to look at 3 different waves: gamma rays, X-rays, and ultraviolet rays. And 3 different gases that protect us: nitrogen, oxygen, and ozone. Now, I'll go ahead and draw them up here. We said first one we're going to consider is nitrogen. We've already done nitrogen on the board, but what does the bond look like for nitrogen? Do you recall? Each nitrogen is 5. Triple bond between them. So, there's my nitrogen. The second gas we're going to consider is oxygen. 2 oxygen atoms. How do they bond? They bond with a double. The last gas we're going to consider is ozone. Ozone's a little bit different. Ozone is a double bonded oxygen and a single bonded oxygen. So we're not really looking at the unbonded electrons right now. We're just considering the bonds for each different type. The bonds in nitrogen, the bonds in oxygen, and the bonds in ozone. Think back to the discussion about relative strength of bonds. Hopefully, again, from yesterday and reviewing when we started, a single bond has a certain amount of energy, but a double bond is stronger, and a triple bond is even stronger, right? You would anticipate nitrogen with its triple bond would be a very strong bond. Oxygen would be a middle bond. And ozone has 2. It has a double bond and a single bond. See that? When I say a bond is stronger, another way of saying that is it takes more energy to break it up. Okay? If a bond is strong, one side is like ionization energy and electronegativity. Ionization energy is looking at it from the perspective of the atom that's losing the electron. Electronegativity is from the perspective of the atom that's trying to get the electron. But you've got to apply at least enough, if not more, energy to take it than the other thing is willing to give in order to keep it. There comes this battle for electrons. In the same way, here the bonds, there's a certain amount of energy that's required to break a triple bond. And if I don't have enough energy to break a triple bond, it's not going to break. But that also means that the energy that would have broken it is still available to do other havoc, to break other things. And what we're talking about here is energy that is on its way to the Earth, where we live, that because of its strength, the energy in that light, it has the ability to kill living tissue. So if that energy was not stopped before it hit us, we would die. For the gamma, we'd all turn into the Hulk, right? Blow up, okay? For the X-rays and then ultraviolet rays. As a matter of fact, when you go out in the summer and you overdo the ultraviolet, what happens to your body? It kills skin cells. And that looks like a sunburn. Okay, so a sunburn is your skin cells being killed by ultraviolet energy that's coming down to the Earth. But what you do get when you lay out or when you're outside, whether you're doing it intentionally or not, is not the full amount of energy that was sent in your direction originally. That there's a natural filtering system that protects us that's in place around the Earth, in the atmosphere. So we've got three different types of energy that are coming down. We're going to consider, first of all, the gamma. Now, the gamma wave, if you remember, was the lowest wavelength, smallest wavelength, which meant it had the highest frequency, which means it has the most energy. And when gamma waves come down, they have enough energy that when they come down, they have the ability, this is gammas, gammas have the ability to break a triple bond. They have enough energy to break a triple bond. What's kind of cool is when the energy from a gamma ray comes down and it impacts a nitrogen molecule, it breaks it up into 2 nitrogen atoms. So the energy that was coming down to kill you gets consumed completely in breaking that triple bond. Okay, so the first thing that happens is that energy no longer is on its way to you. It's been stopped by the nitrogen. But what that energy does then is it breaks the bonds, but it doesn't destroy any matter. It breaks the nitrogen from being a nitrogen molecule into being 2 nitrogen atoms. So what used to be a molecule of nitrogen with a triple bond between it now is just simply 2 nitrogen atoms, but the energy that was on its way to kill you has been dissipated. It's gone because it was used to break that up. Now here's what's cool. What happens when 2 nitrogen atoms are in proximity to one another? What do they naturally do? Because they're a homonuclear diatomic, they naturally don't occur as single elements, do they? Single atoms. They are going to naturally, of their own, reform as a nitrogen molecule. So the energy came in to break them up. That energy's gone, so it's not on its way to kill you. It creates 2 individual nitrogen atoms, which on their own form a nitrogen molecule, which are ready to take on another gamma ray. Okay? So gammas are coming. They're taking these nitrogens that have triple bonds between them. Maybe in your hand you hold a triple like this. Okay? Your hands are both nitrogens, and here's a triple bond between them. The gamma hits them, breaks them apart. The energy's gone. You're saved. They form another molecule. Next gamma hits them. You're saved from another one. They come back together and reform the molecule. And it happens over and over and over again. The energy from the gamma rays are being dissipated and not killing you or turning you into the Hulk because nitrogen is being broken up, but it's also then reforming. Breaking up, reforming. Breaking up, reforming over and over and over again. Okay. That's gamma. Gamma is the shortest wavelength, the highest energy. They're the only one of the 3 we're going to talk about that has enough energy to break up a triple bond. So gammas are the only ones that can do this. The next level were the X-rays. X-rays don't have as much energy as gamma. So when an X-ray comes down, we'll put it to the side here. It doesn't have enough energy to break up a triple bond. Another way to think of it is it can't lose its energy in breaking up a triple bond, so it has to find out something else that it does have enough energy to break, right? And it does have enough energy to break, the X-rays do have enough energy to break a double bond. Not enough to break up a triple. So if you think of it like a pinball machine, if this X-ray is coming down and hits a triple, it bounces off, it goes on, okay? It just continues on because it doesn't have enough energy to do that. But it hits an oxygen molecule. It has enough energy to break up an oxygen molecule. And the same thing happens with oxygen that happens to nitrogen. The X-ray comes down, breaks up this molecule of oxygen, and because it breaks up that molecule by breaking the double bond, it now is no longer on its way down here to kill you, so you're saved from the X-rays because of oxygen molecules. But by breaking up the bond, it forms 2 new atoms of oxygen, which, because they're homonuclear diatomics, automatically reform as a molecule of oxygen and are ready to do it again. And so in the same way, the double bonded oxygen is being broken up by X-rays and continually reforming, continually doing it over and over again. Being broken up by X-rays, rebonding as a molecule, be broken up by X-rays, rebonding as a molecule. And every time that bond breaks, it's stopped that wave from reaching you. So the nitrogens are protecting you from gammas. The oxygens are protecting you from X-rays. X-rays don't have enough energy to break up the triple, only gammas do. Gammas could break up every bond, every single double and triple. But we'll focus on they're the only ones that can break up a nitrogen. So that's where we're going to focus on our attention. The gammas break up nitrogens. X-rays break up oxygens. Go ahead.
How many bonds can you get atoms?
We're going to go as high as a 4. That's yeah. For our octet, you would have 4, right? 4 and 4. Everybody gives 4 and they perform. But practically speaking, for us in here, we're not going to go above 3. So gammas neutralized by triple bonds, X-rays by double bonds, or double bonds by X-rays, and then we have ultraviolet. Ultraviolet is even a longer wavelength, which means it has a lower frequency, which has less energy, right? Ultraviolet, UV. And UVs have enough energy to break up a single bond. So here I might go a UV to break up a single bond. Ultraviolet does not have enough energy to break up a triple, so if it impacts a triple, it keeps going. It doesn't have enough energy to break up a double, so it keeps going. If it runs into ozone, ozone has a double and a single bond. If it finds an ozone, it has enough energy to break up the single bond. Okay. However, slight difference here. When ultraviolet breaks off the single bonded electron, or excuse me, the single bonded oxygen, what's the result of that? Oh, pardon? Right. Because if we've got 2 oxygens that are bonded and we break off the third oxygen, the double oxygens form a molecule of oxygen, and the lone oxygen finds another lone oxygen to form an oxygen molecule. Right? So whereas nitrogen automatically reforms as a nitrogen molecule, and oxygen automatically reforms as an oxygen molecule, ozone is going to reform as 2 oxygen molecules. When 2 ozones get broken, the extra oxygen from each one is going to find each other and form a third. Now, there is a natural process for making ozone, but it's not the same process as the automatic homonuclear diatomic process, which is why we have this issue of the hole in the ozone layer, which is why we're not concerned about gammas and X-rays killing us. What we're concerned about is too much ultraviolet energy coming to Earth. And it's the reason why there could theoretically be holes. And the science on that is, a lot of debate on that. But the process you need to know is that it does not automatically reform as an ozone. Nitrogen reforms as a nitrogen molecule, oxygen reforms as an oxygen molecule, ozone reforms as oxygen molecules. And therefore we don't have the same kind of protection from UV that we have from X-ray and gamma. All right. But this stuff up here in the atmosphere is happening automatically without any, I'll say, thought about it, not on our level, but on God's level. It's kind of like, okay, when you got up this morning, did you have to make sure your heart kept beating? Did you take some time to just think about that for a minute? Say, oh man, I forgot to restart my heart. There's certain things that just happen naturally, and you take advantage of them. We appreciate them, or we may not even think about them, but they keep us alive. They keep us going. This is a naturally occurring chemical reaction that's continuously happening in the upper atmosphere that keeps us from dying because of gamma radiation or X-ray radiation. All right, we've got a few minutes. Let's go ahead and go back to homework from last Friday. Review questions 1 through 8.
It's from chapter 3.
No, 4. The module we're in right now, which means when we get done, like we're done right now, we're done with the module. done teaching through it. Now it's answering your questions on it. Now would be the day when you would typically get, okay, tomorrow is all the review questions. The next day is all the practice problems. The next day is all the extra practice problems. But we've already been working through them, right? Tomorrow you finish up review questions and practice problems. So tomorrow's homework finishes off all of the assignments. But because of that, we're not going to do just one full day of reviewing just review questions. We're going to start now and reviewing the stuff that you should have already turned in. Study guide, review questions, module 4. What are the valence electrons and why are they so important in chemistry? You guessed? Okay. What are the valence electrons? Someone. Pardon? The guesser's going to give me his answer? What was that? We're not all looking at you, are we? No, we're not looking at you. What are the valence electrons? Anybody? We read from the book or go ahead.
I don't know exactly.
Okay.
The electrons that exist furthest from an atom's nucleus.
Farthest from the atom's nucleus are the electrons that are in the highest energy level, right? When you do the electron configuration, they're going to be those electrons which have the highest number, the highest coefficient in front of them. So they're going to be the first, second, third, fourth, fifth, sixth energy level, whatever that is. Now remember, when we fill up the orbitals, as we fill them, occasionally we're going to have these D blocks and these F blocks, but they fill after a higher energy level has already been approached. You've already put something in a 5s before you put something in a, before you put something in the 4D, for example. So if you did your electron configuration, you're going to look at the highest energy level, the highest number that precedes, the 1s, the 2s, the 3s, whatever the highest number is. That highest number tells you, hey, I've put something in that energy level. How many total do I have in that energy level? It's going to be either, we get 8 because the s level has 2, the p orbitals have 6 that combined for 8. Everything else that we have in D's and F's, they may fill later, but they fill lower. Remember? They don't fill in strict level 1, then level 2, then level 3, then level 4, level 5. You go 1, 2, 3, okay, 4, okay, then part of 3, and then back to 4, and then, it starts jumping around. So whatever is the highest energy level, count those up. It's going to be in the row on the periodic table. Like if I'm looking at, bromine, for example, I know it's in the 4th row. My highest energy level is going to be on my 4th energy level. That 4th energy level is going to get its electrons from the S and the P that are in the 4th level. Because S's can hold 2 and P's can hold 6, is a total of 8. That's also where we get the octet rule. For most, but not all, want to have 8 valence electrons to get to their most stable state. Except for a few exceptions, which are hydrogen, helium, lithium, and beryllium, right? The first 4. They're exceptions. They're not looking for 8. They're going for 2. They want to be helium. Okay? But why are valence electrons significant in chemistry? Can somebody translate Neanderthal into contemporary English for me? What's the significance of valence electrons in terms of chemistry? They form bonds, or more generically put, the chemical characteristics of every atom is dictated by its valence electrons. Chemistry is all about this electron interaction we've been talking about. That's all chemistry is. How do these outer electrons react with the outer electrons of other atoms? And so the atom's entire chemical characteristics are determined by its valence electrons. It's a valence electron configuration. That's why elements that are in the same column have very similar characteristics. Why? Because their valence electrons are in the same configuration. Carbon and silicon. We've talked about that as an example of alternative life forms, right? They both have 4 valence electrons. They both form a nice center hub with 4 connecting points around them to form molecules. They behave extremely similarly because they have the same valence electron count, which produces the same valence electron configuration, which produces extremely similar chemical properties. How many valence electrons are in the following electron configuration? Look at number 2. What are the number of valence electrons in this configuration? You don't need to look up there at all. It's right there in the book. They list out the entire electron configuration. Review question number 2 on page 170. Ask yourself, what's the highest energy level on that configuration that they've given you? The 5th. Does everybody see that the 5th energy level is the highest energy level in that configuration? Do you see that? For loser? You got the L? Okay.
It's about. I was counting them all up.
You're counting them all up. So let's do it the easier way. Okay, let's look all the way to the right and work our way backwards and find out what's the highest coefficient in front of each of those S's and P's and D's or F's or whatever you see. What's the highest number you find? A 5. Okay, now look from all the way across and find out how many electrons are represented that are in the 5th energy level. It's a 5s2. That's 2. 4d10. That's only 4. That doesn't count. 5p3. That's 3. The hard part is 3 plus 2 is 5. Okay? That's the hard part of the whole thing. So how many valence electrons are in this configuration? 5. 5 electrons, because they're the only 5 in the 5th energy level. Whew. Should have become a dentist. It's like pulling teeth. Okay. Number 3, the chemistry of life is based on carbon. This means that all the molecules which govern life-giving chemistry have carbon atoms as their principal component. Chemists have often speculated that there could be a life form with a chemistry based on silicon. Why? We just talked about it. Because of all the other elements, silicon is the most similar to carbon. It's the closest with 4 unbonded electrons around it. It's the closest in its electronegativity and ionization energy. It's the most similar to carbon of any other element we have. And so if there is a speculation of other life forms and ours is based on a carbon hub, then theirs could potentially be based on a silicon hub. In the old Star Trek, that's that monster that goes through the walls and anyway.
Wow.
Should I take it before the bell rings or wait? Number 4, what are the noble gases and what makes them so noble? No.
Row 8.
Column 8, noble gases also called inert gases. What makes them significant? They don't react. They're very, very stable.